All right, here we go. Let's look at lesson 2.1, connecting the dots. I'm going to do a couple of these problems that you should have in your notes. So number one says, my little sister Savannah is 3 years old. She has a piggy bank that she wants to fill. She started with 5 pennies. So that's important information. We're going to draw a box around it. And each day, when I come home from school, she's excited when I give her 3 pennies that are left over from my lunch money. We'll use a table, a graph, and an equation to create a mathematical model. So let's think about this. We have our x and y variable. X is our independent variable. So our independent variable, when we have the option, is time. In this case, it's going to be days. And our dependent variable, or our y variable, is going to be the money. So this is important. We've got to decide, is this 5 pennies, is that the first day, or is that 0 days? Well, in this case, it would be 0 days. Because on the first day, her sister would give her pennies, and that would be 5 plus 3, which is 8. And on the second day, your sister's going to give her 3 more pennies, so 8 plus 3 is 11. And we can keep that pattern going. And so when we look at this, look what the change, we kept our change in our x, counting by ones. What did we do? What was the change in y? Well, we were adding 3 every time. So we know that that is an arithmetic sequence. And we know arithmetic sequences make linear functions. So we know when we go to graph this, it should graph a line. And we know that when we go to graph this, we only need the first quadrant because time cannot be negative. And if we're adding money every day, our money's not going to be negative. So we don't need to go left with our x-axis or down with our y-axis. So we're just going to sketch a brief graph. I'm going to count by threes. So on the 0 day, she started with 5 pennies. So this becomes our y-intercept. And that's important. That is where this line touches or crosses the y-axis. Day 1, she had 8 pennies. Day 2, she had 11 pennies. Day 3, she had 14 pennies. So then the question becomes, do we connect the dots? Is the data discrete or is the data continuous? So we like to think of discrete data as that is something that is being counted. And when we count, we tend to only use whole numbers. Continuous data is data that can be measured. So think about measuring the length of a piece of a 2x4. It could be a whole number. It could be 8 feet long. But you could cut it and measure it, and it could be 7.5 feet. It could be something like 7.123 feet. And so continuous, we kind of think of it as things that can be broken down into parts. Whereas discrete, we think of as it should be whole numbers, things that can't be broken into parts. And so this whole idea of discrete and continuous comes into play when we're graphing, because discrete tells us we don't connect our points, or don't connect the dots, or continuous tells us we should. And in this example, we're talking about money, and the sister gives 3 cents every day. And it's either the sister gives the 3 cents or she doesn't. Little Savannah isn't earning partway through the day here, halfway through the day, Savannah's sister's not giving her 1.5 cents. So this data is actually discrete because we're not breaking up a day into parts, and we're not breaking up that 3 cents into parts. So then the next thing was, let's write an equation. Well, we know it's arithmetic, we know it's linear, and we know the general form of a linear equation is y equals mx plus b. M is what we're changing by, that is our slope. B is where x is 0. So the equation for this would be y is equal, and what were we adding every time? We were adding 3. And where did we start? She started with 5 pennies. So that is the equation for this data. Let's look at an example of continuous data. Our family has a small pool for relaxing this summer, and it holds 1,500 gallons of water. When I had 5 gallons of water in the pool, decided I didn't want to stand and watch it fill, so she timed it. What she found out is that it was filling at a rate of 2 gallons every minute. So the easiest thing to start with is let's create the table and then build from there our graph and our equation. So our independent variable is time again, and in this case we're measuring it in minutes. And our dependent variable is the number of gallons of water. So this actually represents 0 minutes have gone by. She hadn't started timing this until she came out and saw that there were 5 gallons of water. So she didn't start recording that until it already had 5 gallons in the pool. So after 1 minute, she now is going to add 2 gallons. And so now she has 7 gallons in the pool. 2 minutes, she's adding 2 more gallons. And there's 9 gallons in the pool. And we keep going on. So we see that we're adding 2 every time. So that makes this an arithmetic sequence, which makes this a linear function. So our graph, we would have minutes down here. We would have number of gallons of water going up the side. So at 0 minutes, we'll just count by 3s again to estimate. At 0 minutes, she had 5 gallons of water. 1 minute, it was 7, 9, and then 11. So these look like they should form a line, so that means we graphed correctly. So now we've got to decide, is it continuous or discrete? So we got to ask ourselves, are we just counting, or can we have parts of stuff? So it makes sense if I look at minutes, I can break minutes down into seconds, milliseconds, so I can have parts of minutes. When I look at the gallons, can I have parts of a gallon? Can I say that? At some point, she has 5.5 gallons of water in there. At some point, she has 5.28 gallons of water in there. And I can, and it makes sense, so that makes this data continuous, because I can have parts of a minute and I can have parts of a gallon. So we would connect, continuous means connect the points, because that means it can be everything in between those points as well as those points. So an equation for this would be y equals, what are we changing by? We're changing by 2, so that becomes our slope, plus, where did we start? Where x was 0, we started at 5. So this equation is y is equal to 2x plus 5. And now we're going to look at an example. This one is going to be exponential. Because if I look at the problem, I see a percent. As soon as I see a percent, I know that that's geometric. And I know that geometric makes an exponential function. So, And this girl is a little more sophisticated than her little sister, and she puts her money in a bank account that pays 3% interest at the end of each month. She started the account with $50. We're going to use a table, a graph, and equation to create a mathematical model. So again, time is going to be our independent, and money is going to be our dependent. So at 0 months, she started with $50. So after 1 month, we've got to figure out how much money she has in this bank account. Well, remember, when we see interest, we know it's either going to grow or be smaller. They're paying her, that means she's taking 100% of that $50 she started with, plus they're adding 3%. So to find the first month, you're actually going to have 103%, which turned into a decimal is 1.03. So 50 times 1.03 is $51.50. So if I continue filling out this chart, I just keep multiplying by 1.03. So on month 2, she would have 53.04. On month 3, she would have $54.64. On month 4, she would have $56.28. And if we were to graph this, again, we only need the first quadrant because time is not going to be negative. And she's gaining money, so she's not losing it, so we don't need the negative y's. So we'll start this at 50, and we will count by ones. So at the end of the first, well, let's talk about the 0 month. It would be the 0 month, because this is where she started. At the end of the first month, she has $51.50. At the end of the second month, she has a little over 53. At the end of the fourth month, she has a little over 54. At the end of the fourth month, she has 56. And if we look at this, it kind of appears to be linear. It should be more curving this way if we were to connect it with a line. However, this data is discrete because of this statement right here. If I take my money out before the end of the month, I don't earn any interest for the month. So that means that it can't be anything in between these 2 points. It can't be a half of a month or a third of a month, or she doesn't get the interest. It has to be interest. It has to be the whole month or nothing at all. So this data is discrete. We would not connect the dots in the graph. And so much like we know that the linear equation is y equals mx plus b, we should know that the exponential equation is y is equal to ab to the x power, where a is our y-intercept, and in this case is 50. And what are we multiplying by each month? Well, we are multiplying by 1.03, and we're taking it to the x power. And so that is our equation. So we're going to skip the rest for this video, the rest of these examples, and I'm going to do one example from the Ready, Set, Goes. Ready, Set, Goes 1 through 8 is you've got to tell if it's arithmetic, geometric, or neither. Remember, arithmetic is your adding. Geometric is your multiplying. So if we're adding going to the right, we go backwards by subtracting. So we would check to see if this is arithmetic by doing -500 minus 100, and negative 500 minus 100 is negative 600. And then we would do 100 minus negative 20, and that's 120. Those numbers didn't work out to be the same, so it is not arithmetic. So we come back and try to see if it's geometric. Geometric means we're multiplying going to the right. So we would divide to go to the left. So if we do negative 500 divided by 100, that is negative 5. And if we do 100 divided by negative 20, that is also negative 5. So that means our common ratio is negative 5, and since we have a common ratio, that makes this geometric. Then 10 through 15 was deciding if this was a discrete or continuous relationship. So the hair on your head grows a ½ inch per month. So would I connect the dots? Could I break the month down into parts? Could I measure my hair after 1 day? Could I measure my hair after 2½ days? I could. That makes sense. If it grows a ½ inch per month, could I measure on the first day that it grew 0.008 of an inch? Eighth of an inch. Yes, that makes sense. So that makes this continuous data. For every ton, number 11, for every ton of paper that is recycled, 17 trees are saved. We are counting this. It's 1 ton saves 17 trees. I could save ½ a ton, but that would mean if I do 17 divided by 2, I'm not saving 8½ trees. I either save a whole tree or I don't save the whole tree. So that makes this data discrete. And then 16 through 21 is unit rates. You have to set up proportions. And you have to do these problems in order because you have to have information from number 16 to answer number 17. Apples are on sale at the market, 4 pounds for $2. What's the price in cents for 1 pound? Well, it's 4 pounds over $2 is equal to, I want 1 pound over X amount of dollars. So we cross multiply. 2 times 1 is 2, and that is equal to 4 times X, which is 4X. How do I get X by itself? I divide by 4. So what's the price for 1 pound? It is 50 cents a pound, because 2 divided by 4 works out to be 0.5. And then 22 through 30, these are all one-step equations. What's the inverse operation of multiplying, dividing? So we have to show our work. We have to show that we know that we divide both sides by 6. 6 divided by 6 leaves us with 1x. 72 divided by 6 leaves us with 12. So x is equal to 12. And this is how we have to write our answer. We learned in class that if we have a fraction, we multiply by the reciprocal. So we would multiply by 2 over 1 on each side. So x is equal to 17.31 times 2 over 1, which is 34.62. So that are some examples and part of the notes for Module 2, Lesson 1.